Hey, seventh grade. Okay, so we've talked about two different ways that we can tell how old something is. Absolute dating and relative dating. Remember, relative meant we're comparing it to other things. Absolute means we find an absolute age for it. One of the ways to find absolute dating we're going to talk about in the upcoming Nearpod, and that's called carbon dating. It's a pretty complicated topic, but we're going to break it down into a way you understand. So you guys already know that everything is made up of atoms. That's not new news for you. So here we're dealing with a specific atom called carbon, specifically carbon 14, which when you get to 8th grade in high school, we'll talk about what the 14 means. But what we care about now is that this carbon has 6 protons and 8 neutrons. So this carbon atom, our bodies have. All living things have carbon. Your body makes carbon. Your body uses carbon. But over time, after you've died, you no longer make carbon. So that carbon just sits around in your dead body or a dead animal's body or a dead tree's body, whatever we're looking at, and it slowly turns into nitrogen 14. So you go from being carbon to nitrogen. So scientists are able to look at an organism and scan it to see how much nitrogen is in there versus how much carbon is in there. So if I found a dead tree, I could scan that tree and see, does it have more nitrogen or more carbon, and figure out how old it is based on how much carbon has changed into nitrogen. So looking at this little thing, at the beginning, we have the same amount of carbon as that's in the atmosphere all around us because our body's constantly making carbon. We're using carbon. The trees around us are using carbon. It all gets mixed. But when your body dies, or a tree or an animal dies, they don't make any more carbon. So all it does is change into nitrogen. So when we look at this, we can calculate how long it takes carbon to change into nitrogen. And that's going to be around 5,730 years. So in this case, we have a stick that just broke off of a tree. That means it's not living anymore. And it's 100% carbon. Then we find a different stick, and it's only 50% carbon. So it's half carbon, half nitrogen. And that tells us that it's going to be around 5,730 years old. Then we come back a long time later, and the stick is only 25% carbon, 75% nitrogen. And that tells us that it's gotten significantly older, 11,000 years old. And then we come back and it's even older. So now it's only 12.5% carbon. And that shows us that it's 17,000 years old, much, much older. So when we look at this simulation, if we could pretend that we could just throw atoms in a bucket, which we can't for real, but we're just pretending. So here I've got 12 of these carbons, and we see that right around this mark, 12 of them turned into nitrogen. Sorry, we have 10 of these carbons, and right around this halfway mark, 5 of them had changed into nitrogen to make it half. Half of them had changed into nitrogen. If I add more, we can see that it goes down this train. Half of them are still carbon. Right around the half-life mark, half of them have become nitrogen, and the rest spread out. Carbon is what we normally test on, but you can also test on other elements like uranium and lead, because uranium does the same thing as carbon does, except it changes into lead. So once again, when we're dealing with half-life, we want to know how long does it take for half of the carbon to turn into nitrogen. And it only starts turning into nitrogen once the organism dies. So if I add a whole bunch of carbons to this, and we watch it go, this will hit the halfway mark right around when we got to our half-life line. We can also see this on a chart. So notice we're looking at our half-lives. Here's our first half-life, right around that 5,700. Here's our second half-life. If we put our carbons in, there we go, we can see that at the first half-life, it's going to divide in half. And then it's going to hit halfway again, and half of that number again up here.